This lecture is an introduction to chemical bonding as well as an introduction to how we name compounds. The first thing I want you to realize is that chemical bonds are not a physical entity. Chemical bonds are simply a very strong attraction between two atoms. And the type of attraction is an electrostatic attraction, which means attraction between opposite charges. Usually we classify a compound and the chemical bonds it has as either ionic or covalent, but in reality, chemical bonds lie on a continuum where on one end we would call them, let's say, pure covalent, and on the other we would call them pure ionic, and the majority of chemical bonds would lie in between those ends. So throughout the semester, we'll be talking about, as we get a little bit further on, covalent bonds, and you will see that there are actually two types of covalent bonds. There's what we call the nonpolar covalent, and that is when electrons, valence electrons, outer electrons between two atoms are shared equally, like these two nice dogs are sharing the bones. Polar covalent is the valence or outer electrons are shared, but not quite equally. One of the atoms is pulling on them a little bit more than the other. And then finally, there is the ionic bond when there is no sharing at all going on between the outer electrons of the two atoms. And as a matter of fact, one of the atoms actually takes one of the electrons away from the other. So what makes a bond polar or nonpolar or ionic? Well, the first thing to understand is that an ionic bond is the most polar of all bonds. So when we say polar covalent, those are not yet as polar as an ionic. So ionics are the extreme of polarity. What is polarity mean? That just means there's some type of separation of charge, okay, which means the electrons aren't completely evenly distributed. So the more polar a bond is, the more it progresses toward an ionic bond. And what makes that separation of charge or polarity? The greater the electronegativity difference between two elements is. Now we come to, there's a lot of vocabulary here, so you probably want to jot it down. What is electronegativity? That is the attraction for extra electrons, okay? So the more electronegative something is, the more it wants extra electrons. So if you have two atoms that are coming together that have very, very different electronegativities, the more electronegative atom is probably just going to snatch an electron from the less electronegative. If you have two atoms that come together with very similar electronegativity, they will probably play nice and share roughly equally and make a covalent bond. So how do you tell by looking at a chemical formula like this whether it is an ionic bond or a covalent bond? Ionic bonds occur between metals and nonmetals and involve the complete transfer of electrons from one of the atoms to the other. So remember, the metals are to the left of the stair step. So if you have a metal in a compound, it is an ionic compound. The metal ion has a tendency to always give up the electron. Their metal ions are not very electronegative. And what happens when you give up an electron? What's left over becomes positively charged, and that's called a cation. The nonmetal involved in an ionic bond, those are the atoms to the right of the stair step. Those tend to accept extra electrons, and when you accept an extra electron because they have a negative charge, you become an anion. So ionic compounds are made up of cations and anions, strongly attracted to each other because of their opposite charge. So the ionic bond itself is simply a very strong electrostatic attraction between oppositely charged ions. And because of that really strong attraction of the oppositely charged ions, ionic compounds end up being a mass rather than one individual molecule, like let's say water floating around. You have many of the cations and anions all attracted to each other in this three-dimensional lattice. Covalent bonds, on the other hand, occur between two or more nonmetals. So that is two elements to the right of the stair step. So water, for example, would be covalent. Even though hydrogen is to the left of the stair step, it is a nonmetal. Chemists weren't really sure where to put hydrogen. It's a little unusual. So covalent bond, again, just to remind you, there is no complete transfer of electrons as there is with ionics. The two bonding atoms share their valence or outside electrons. When two atoms come together and make a covalent bond, we call that compound a molecule. Okay? So when somebody says molecule or molecular compound, they are talking about covalent bonds. Ionic compounds, on the other hand, for example, table salt, sodium chloride, because we can't isolate one individual NaCl unit. Remember in the last slide I talked about how a whole bunch of cations and anions all packed together because of the strong attraction of opposite charges. So you don't really have like a water molecule that just kind of floats around by itself. You have a whole bunch of these NaCls packed together. So because they aren't individual molecules, we call them formula units. So if you see the label of formula units, you know it's ionic. I don't want you to let it confuse you. It simply means molecule, but for an ionic compound. There are two types of chemical formulas, like shorthand for showing you what a chemical is. There is an empirical formula and a molecular formula. The molecular formula is what you're used to seeing. Let's say if we were doing methane gas, it tells you exactly how many of what type of atom are in a compound. Empirical formula is something that may be a bit new to you. Empirical formula is simply this, simplified version of the molecular formula. So, for example, if we had a compound C4H8, it happens to be butane. That's what they put in cigarette lighters, that liquid stuff that burns. Can you simplify that mathematically? Well, yeah, you could divide both subscripts by 4, right? And if you did so, you'd get CH2. So that is the empirical formula of C4H8. So what you do is you look at the subscripts. If you can mathematically simplify them, divide them by the same factor, then do so if you're trying to get the empirical formula. Now, sometimes the empirical formula and the molecular formula are the same thing. So, for example, carbon tetrachloride, you can't simplify that any further. So the empirical and molecular formula are the same. Same as for water. Okay, can't simplify it anymore. Well, if you're like me at all, I would be asking, okay, why do we need an empirical formula if it's not even the real formula? It turns out that if you have a substance and you don't know what it is, you hand it over to an analytical chemist, and they have all sorts of machines they can use to analyze the composition of that sample. And typically a machine will simply give you the ratio of elements in a sample. That machine doesn't know, it may know that there's one carbon for every two hydrogens, but it doesn't know the total number of carbons and the total number of hydrogens. It usually just gives you a ratio. And so that is why empirical formula is so commonly discussed with chemists, because the equipment, the machines, typically give us empirical formulas. All right, we're going to start talking about naming or nomenclature in a bit, but have 3 or 4 slide diversion. Elements, most of them exist as single atoms. So, for example, you have carbon. Of course, all the ones I'm thinking of now exist as diatomic. Okay, helium, lead, tin. Okay, those exist as individual atoms. However, there are several elements that exist in nature in molecular form. What do I mean by that? Well, when you're talking about a molecule, you're talking about more than one atom. So let's look at these. An element that exists single atoms, okay, would be neon, for example. Okay, what am I talking about when I say elements that exist in nature as molecular? Well, for example, oxygen. In nature, you see oxygen, 2 of them, O2. Okay, you don't see one single oxygen atom in nature. It's just much more stable as O2. As we get into naming and start talking about chemical reactions, it's important to know which elements do exist as a molecule rather than a single atom. And there are 7 of them that exist as diatomics. And go ahead and commit these to memory. Jot them down, make a note. This is a little bit obscure, but just so you aren't quite as startled if you see it in a chemical reaction, phosphorus actually in nature exists with 4 phosphorus atoms bonded together and sulfur with 8. So in high school, you may have had a way to remember these 7 diatomics. I think a common way I've heard is this funky name, Hofbrinkel. Okay, so hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, Hofbrinkel. So if that helps at all. I think a really cool way to remember it, remember that there are 7 diatomic elements. And so start with number 1, which is hydrogen. Then go to number 7, because there are 7 diatomics, and draw a figure 7 on the periodic table. As you draw figure 7, you see you have now covered all 7 of the diatomic elements. Here's a summary of what we've learned about ionic compounds. Ionic compounds are made up of positively charged ions called cations and negatively charged ions called anions that are electrostatically attracted to each other. The anions and cations come together to make a compound that has an overall neutral charge. Okay? So NaCl, you could look at the charge on the individual cation, which is +1, and the individual anion, which is -1, but always the overall sum of the plus and minuses are 0. 1 unit of an ionic compound is called a formula unit, not a molecule, a formula unit. Ionic compounds are probably trickier to name than covalent because of the various charges the cations and anions can have. So there are some elements that when they become an ion always end up with the same charge. And so it's easiest to memorize those charges. So remember I've said that metals will typically lose an electron to become a cation or positively charged ion. And so the metals that get the same charge every time they become an ion are the ones in the group A groups. So group 1A over to the far left, those ions, when they become ions, always have a charge of +1. Group 2A ions have a charge of +2. Skip over to group 3A, and when they become ions, they have a charge of +3. Now look for a minute at the nonmetals over on the right-hand side of the periodic table. Now remember, they tend to accept extra electrons. They're electronegative. They accept extra electrons, so they tend to become anions. I'm going to cross that out. And so it's kind of a mirror image of what we just made with the metals. So 5A group will tend to gain 3 extra electrons, and the ions therefore have a charge of -3. The oxygen group, when they become ions, has a charge of -2. The halogens end up with a charge of -1, and the noble gases to the far right do not become ions. Okay, they're very stable as they are, and so they don't tend to make chemical bonds and don't become ions. While you should memorize the charges that ions have in the A groups, you don't have to memorize the following. Transition metals here in the middle of the periodic table, as you can see, most of them can have more than one charge when they become an ion. And there are a couple of rebels, tin and lead, that behave like transition metals, and they have variable charges. So when we get into the rules for naming ionic compounds, if it has a transition metal or tin or lead, there's an extra step we're going to have to take. Iron, for example, can have a +2 charge or a +3 charge when it's in an ionic compound. Here are just some examples. And so you've got to differentiate the name of these two compounds so that the reader knows what you're talking about. Starting with the simplest type of ionic compound to name, binary ionic compounds. Binary means 2, so compounds that have only 2 different elements in them, not 3 or 4. Okay, they're the easiest to name. For example, table salt has only 2 different elements. The rule for that is the metal is named simply by the element name. So Na is sodium. You don't do anything to it, just write the name of the element. The second nonmetal in the ionic compound starts out being named the same, so this is chlorine, but instead of the ending that it has as an element, you change the suffix or the ending to IDE. So instead of chlorine, it would be chloride, IDE. So the name of NaCl is sodium chloride. Here's a couple more simple ones. Potassium chloride, calcium oxide. So those are binary ionic compounds. Now here comes a little bit more complex, so you may want to make notes of this for yourself. If the ionic compound has a transition metal or lead or tin, remember there are rebels, okay, they can have variable charge. So because of that, you need to let the reader know what the charge of the metal is in that particular compound. And how chemists have decided to do that is whatever the charge of the transition metal is becomes or is designated by Roman numerals in parentheses after the name of the metal. So notice there's a +2 charge, so that the name of anything with iron and a +2 charge is iron, parentheses, Roman numeral 2. If there's a charge of 3, the Roman numeral 3. So here's a summary of naming a compound with a transition metal. You still name the metal the same way. So let's do PbCl2. So again, even though lead is not a transition metal, it behaves like one. So we would start naming that the same, whoopsie, which is lead, okay? Then hopefully you remember that lead behaves like a transition metal, so I just write parentheses to kind of prompt myself to figure out the charge. And then the nonmetal, again, is named with the ending IDE. So that's chlorine, so we know the end of it's going to be chloride. Okay, IDE. Now, the tricky part is, how do you figure out the charge that lead has? Well, almost always you're going to figure out the charge of the nonmetal in the compound, because those are almost always in the A groups that have the same charge all the time when they become an ion. So I don't know if you remember, but chlorine is a halogen. That's in group 7A, and all of the elements in 7A, when they become ions, have a charge of -1. So if each chlorine atom, chloride ion, has a charge of -1, there are two of them, right? The overall charge, negative charge in this compound, is -2. Remember I said that ionic compounds overall have to have a charge of 0. They have to be neutral. So what does the charge on the lead have to be in this compound so that it's neutral overall? It has to be +2, right, to counter the negative charge. So the Roman numeral 2 goes in parentheses here, and this is called lead 2 chloride. So here's what I just babbled on about in writing, if you want to kind of go through it more slowly. In this case, chromium is a transition metal. And again, you always go to the nonmetal part, figure out its charge first. Bromine is also a halogen, which has a charge of -1. There are 3 bromines. So the overall charge, negative charge in this compound is -3. So in order for the overall charge of this to be neutral, chromium has to be +3. So the name of this is chromium 3 bromide. Now I'm hoping this isn't a new concept for you. This is the third type of ionic compound, and it's an ionic compound that contains a polyatomic ion. So poly means many, right? So if you have, instead of, let's say, lead bromide, what if you had something funky like lead and then just strange like that? So instead of having one atom for your anion, you've got bromine and oxygen, more than one. That is a polyatomic ion. Okay, so the whole BrO3 is an ion, and there are 2 of them, but it's a polyatomic ion, whereas bromine by itself is just, actually, if you want to be fancy, monatomic ion. So polyatomic ions have their own unique names. The basic ones you'll just have to memorize, and I will give you a list of the ones you need to memorize. But for now, you could just, I'll actually upload a list of them. I'm sure there's a list in your textbook also of commonly used polyatomic ions. So let's look at an example. NaNO2. Well, Na is sodium. That's not a transition metal, so we don't have to worry about parentheses and Roman numerals. NO2 is a polyatomic ion because it contains more than one atom in it. And you just have to know the name of NO2. Okay, it happens to be nitrite. So the name of that compound is sodium nitrite. So you just plug in whatever the name of the polyatomic, and that's just a matter of memorization. Okay, so I did have a chart. You probably want to print this out, The more common ones, I'm going to go ahead and circle. You might even want to make a note card of them because you will have to at some point commit these to memory. Okay, so that's good for now. Here's a summary of the kind of convoluted naming rules we just went through. So always write the name of the cation first, and the cation name is always simply the name of the element. Okay, that's pretty easy. If the anion is a single element that is not a polyatomic ion, change its suffix to IDE. If the anion is a polyatomic ion, just write whatever the name of that polyatomic ion is. And the last rule is if the cation is a transition metal or lead or tin, you must write the charge of the metal ion as a Roman numeral in parentheses. So you may want to jot these rules down. It's a nice little summary. See if you can name these on your own. And I encourage you not to just go right ahead and look at the names I've given them because, of course, it'll be logical. Yeah, I can do that. But not until you sit down and try to figure it out yourself do you realize how tricky it can get. So I would put the video on pause and see if you can name these. All right, so the first one, K2SO4, okay, we know it starts with potassium. Hopefully you identified that SO4 is a polyatomic ion, and you have to look at your handy-dandy polyatomic ion chart, which I hope you've printed out, and you'll notice that SO4 is called sulfate. That's it. Potassium is not a transition metal, so you don't have to worry about that. The second one, okay, barium is not a transition metal, and this is another polyatomic ion. OH is a very common one, and its name is hydroxide, so it is simply barium hydroxide. Here's one that you actually need to put a little more thought in. Hopefully you identified that iron is a transition metal, so it needs the parentheses and a charge. And since chlorine is a halogen in 7A, and when they become ions, have a charge of -1, there are 3 chlorines, so the overall negative charge in this compound is -3, which means the iron has to have +3 so that the overall charge is neutral. What if I asked you to go in the opposite direction? What if I gave you the name and asked you to write the formula? The single most important tip I can give you is that when, and you probably want to write this down, when you are writing an ionic formula, it's a 2-step process. Okay? The first step is to write both ions, the cation and the anion, with their charges. And the second step is to crisscross charges. What the heck do I mean by that? You may have learned that in high school. If not, I'm going to show you. So let's do what I just said. All right, potassium. Okay, I'm going to look at my periodic table. That's K. It's in group 1A, and I'm hoping on your periodic table you wrote what the charges of the A groups are. If not, you can go back to that slide. But group 1A always have a +1 charge. And sulfide, it ends in IDE, which means it's just an element from the periodic table. Okay, so if you see that ending IDE, it's probably a binary compound. Sulfur, that's in group 6A. It has a charge of -2. Okay, here's what I mean by crisscross. You take whatever the charge is on the metal, and it becomes a subscript on the other element. Whatever the charge on the nonmetal becomes a subscript on the metal. So your formula, your chemical formula is K, and we've got a 2 here now because we crisscrossed, and sulfur has a 1. So if there's a 1, you can just leave it off. It's assumed that it's 1. So here's the formula, though, for potassium sulfide. Before you try the other ones, I want to point out hydrogen carbonate is a polyatomic. So you're going to have to look that up. Perchlorate is too. How do you know just by looking that they're polyatomic? Well, if they don't end in IDE, they're not an element. They're not a single element, I mean. So notice how these end in ATE, 8. So that means they're both polyatomic ions. So go back to the polyatomic ion list. See if you can identify what hydrogen carbonate is. It's also called bicarbonate. And what perchlorate is. And see if you can write these formulas. All right, so the correct formula for calcium hydrogen carbonate is right here. You can see I did the 2-step process where I wrote the cation and anion with their charge, and then I crisscrossed. Same with nickel perchlorate. Wrote the individual ions with their charges and then crisscrossed. It's very, very important that you practice these names and formula writing over and over and over until it becomes quite simple. So go to the problem solving folder in our D2L and practice as many as you can. You are going to be relieved now because naming covalent compounds, remember they're called molecules or molecular compounds, are so much easier than ionic compounds. So the one thing that's mainly different between naming covalent and ionic compounds is that whereas ionic compounds, the cation and anion can only combine in a certain ratio, and that depends on the charges of each of them. Molecular compounds, covalent bonds, can make in all different types of ratios. So look here at all the compounds that nitrogen and oxygen can make covalently. Okay, it's a 1-to-1 ratio, 1-to-2, 2-to-1, 2-to-3. So because of that, prefixes must be used when naming covalent compounds, and that's the key difference between covalent and ionic. So here's the general rule. If you have a covalent compound, let's just look at water, H2O. So the common name is water, but let's think of what its chemical name is. First, you need a prefix, which tells you how many of the first element there are. Here are the prefixes. Make sure you memorize them. So look at the formula for water. We have 2 hydrogen atoms. The prefix is di. So you would write dihydrogen. Okay. And so we've got this part done. And then you need a prefix for the second element, which is oxygen. There's only 1 oxygen. So we are going to then say mono. Now, look here. So even though that's called oxygen, in a covalent compound, the second element is named with the ending IDE. So instead of saying monooxygen, you would say monooxide, IDE. Okay? So the technical name for H2O is dihydrogen monoxide. I would not count this wrong, but if you have 2 vowels together in a covalent name, the custom is to cross out the first one. So it would, instead of being monooxide, it would be monoxide, like carbon monoxide. But again, I wouldn't mark that wrong. Here is practice for you. These are pretty simple, so I would shut off the video and make sure you can name these by yourself. How did you do? Did you get them right? Now, there's a little obscure rule that you need to know. You might say, why wasn't this monophosphorus trihydride? If there is only one of the first element, so if there is only one atom okay, of the first element in a covalent compound, leave mono off. Okay, leave the word or prefix off. Okay, so that's just phosphorus trihydride. Same here, carbon monoxide. Okay, so instead of saying monocarbon monoxide, if there's only one of the first, you leave off the prefix, and it's carbon monoxide. Dinitrogen trioxide. Almost done. It's been a long video. So going the other direction, so if you're given the name, can you write the formula? And again, these are so much, I think they're so much easier than Ionic. You just have to make sure you memorize the prefixes. So go ahead and make sure you can name these on your own, and the answers will be on the next and last slide. And here are the answers. How'd you do? Dinitrogen heptachloride, carbon tetrachloride, and dihydrogen monoxide. That's it for this video.